So I'm not going to rush, but I'm going to go at a fast pace, just because I didn't get a chance to review. I sent these, the PowerPoint out, just in note form, but there's some things I just want to cover because it's going to be on the midterm. A lot of these are just facts. This is all 101 stuff, right? I said 93 million miles. I made a point. That's a 1 AU. But I just wanted to talk about our orbit around the sun, about 575 million miles. That's an ellipse. We are not perfectly centered in the ellipse. We're a little off to one side, right? Ellipse is an oval. Because of that ellipse, right, we go into that whole Kepler's law. There's a moment in our orbit where we're close to the sun and a moment when we're further away from the sun. We're in an aphelion and a perihelion. A para meaning near, and aphelion meaning a little further away. In that orbit, we travel at a velocity of about 67,000 miles an hour. So this is what we cover in a day. Just so you have an idea of how fast we're going around the sun, 1.6 million miles a day. And all these other things you get, right? Those are all in the cosmos, billions and billions, that stuff. And any one of these shows we watch talks about our galaxy and our Milky Way, and our Milky Way is packed with stars, and we are one of 200 billion. Yes, I understand. But our Milky Way itself, its size from arm to arm, or as a spiral galaxy, from arm to arm is about 100 to 120,000 light years across. So if we're 120,000 light years across, 100,000 light years across, from the center to the edge is 50 or 60,000 light years, depending on where you are in the spiral. We find ourselves at around 30,000 light years from that center. And the spiral arm that we're in is called the local Orion arm. When we talk about light years, we're talking about in terms of distance. I know they do a lot of kilometers in the book, but we're just used to miles. I wish it was a universal. America just didn't get on board with that. But 5.87 and on, but we're going to I always round it up to make things easy. So about 6 trillion miles is a light year, right? And our sun, in its orbit around the Milky Way, takes around 225,000 light years. If we're looking, right, from the center, there's a black hole. We are about 28,000, 30,000, give or take, light years, again, depending on where we are in our orbit around the center. The local Orion arm, so this would be us. So when we're in the Milky Way or when we're on Earth and we're looking out, we're staring into this arm. This is what we see. We're not looking into the whole of the Milky Way. We're looking into our little section of the Milky Way, right? Center, 30,000 plus light years here. Our local Orion arm. So when we look out, this is it. This is, you see this haze, right? Our own background nebula. The deep field. I'm just gonna. I know I said play it. I put it in there. But I'm gonna hit it. I believe this. Maybe this isn't the one. Oh, I hope this is the one. I think it might not be. There's two. I erased one. I know I'm talking to you as if you're here. Why not, right? Danny DeVito is a funny character. Let me pause my background music here. You're seeing what I see, folks. Alright, skip this. Yeah, no. Although this Pink Floyd jam is awesome, I'm gonna pause. This was the wrong one. Back to this. It was this one. Yes, wonderful. Gregorian chant in the background. Let's go full screen on this. Okay.
Astronomers in 1996 attempted to do something extraordinary.
You know,
They pointed
Neil
the
deGrasse,
Hubble Space
I hope you
Telescope
watched
into
this.
a part of the sky that seemed utterly empty, a patch devoid of any planets, stars, and galaxies.
all right.
This area was close to the Big Dipper, a very familiar constellation, and the patch of sky was no bigger than a grain of sand held out at arm's length. This was a somewhat risky move by the scientists. After all, observing time on this telescope is in very high demand, and some questioned whether it would be wasted trying to look at nothing. there was a real risk that the images returned would be as black as the space at which it was being pointed. Nevertheless, they opened the telescope and slowly, over the course of 10 full days, photons that had been traveling for over 13 billion years finally ended their journey on the detector of humanity's most powerful telescope. Their feeble signals collected almost one by one. When the telescope was finally closed and the images were processed, the light from over 3,000 galaxies had covered the detector,
All right, I'm going to stop
producing
there.
one of the most profound and humbling images in all of human
You
history.
bet it is. All right. Just things I wanted to discuss that I don't know if you picked up. I'm sure you did, but I just want to reinforce. They aimed this at a piece of sky that was no bigger than a grain of sand. So that's their field of view. That's it. Just a grain of sand. Now, after 10 days of this, right, the shutter open, right, camera open a shutter, lets all that light in. So Hubble was just focused on one spot in the sky for over 10 days, and this is when they finally developed the film. This is what they saw: 3,000 galaxies. Now, every dot on this screen is a galaxy. So every dot on the screen represents something similar to our own, depending on its age or its galaxy type. But nonetheless, every dot here has billions of stars within it. That's one grain of sand in the sky. Hubble is limited, so there's more. There's only what Hubble can see. And now what you're looking at on the screen is 3,000 galaxies in one grain of sand. Now imagine the entire sky full of grains of sand surrounding the Earth, right? Not just the entire sky, 360 degrees worth of sky full of this, and each little pixel of sand is 3,000 plus galaxies. Oh, but that's not it.
Every single spot, smear, and dot was an entire galaxy.
Yes.
And each one containing hundreds of billions of stars. Later, in 2004, they did it again, this time pointing the telescope towards an area near the constellation Orion. They opened the shutter for over 11 days and 400 complete orbits around the Earth.
So they added a day.
Using detectors with increased sensitivity and filters that allowed more light through than ever before, over 10,000 galaxies appeared in what became known as the Ultra Deep Field.
I'm going to pause the Ultra Deep Field.
Represented the farthest we've ever seen into the universe.
Pause. So now the initial photograph was 3,000, and they amped up the power of the telescope, let it sit for another day with the shutter open, and now they have 10,000. So again, every pixel of sand in the sky has 10,000 galaxies in it. So if our eyes were calibrated to the strength of Hubble, if you looked up in the night sky, everywhere you looked, the night sky would look like this. And this is only limited to as far as Hubble can see when they launch James Webb. Whenever they launch James Webb, it's an incredibly complex piece of machine, so it continually is delayed. That should triple what Hubble is capable of seeing. This is the Hubble Deep Field. That's why they say, look, before this, they didn't see this. This was unknown. This level of photography, or this level of awareness of what was out there before this particular picture was taken. The Hubble Deep Field changed the way that we see ourselves in the world. All right, I'm going to pause here.